USD 20 million from MITI, DST, UKIERI, MOE, AKA, IUSSTF, and KPMG. He has more than 300 peer-reviewed publications and has filed 13 patents, with 4 granted. He has supervised 15 defended, submitted PhD theses. His research interests are in the broader areas of communications, non-Gaussian, non-parametric signal processing, machine deep learning with applications to communication, and photonics. He is a reviewer for IEEE, Elsewhere, Wiley, Springer, and IET. He is currently senior member of IEEE, fellow IETE, and certified SCRUM master. He was also the general co-chair for IEEE ANTS 2018 and general vice chair for IEEE ANTS 2017. He has served as founder head of Center for Innovation and Entrepreneurship, associate dean R&D, and dean academic affairs. He has delivered many talks, tutorials, and conducted faculty development programs for the World Bank's NPIU TCube3 and invited talk at WWRF 46 Paris. He is currently associate editor for IETE Technical Review, Frontiers in Communications and Networks, Frontiers in Signal Processing, and IEEE Wireless Communication later. Now I welcome Professor Vimal Bhatia sir to deliver his talk.
Okay, thank you very much indeed. It's a pleasure to be here. Yeah, so because I'm on travel at the moment, so might be some disruption and things, but let's see how it goes. I'm using actually not my usual laptop today, so let me share my screen. And I'll switch off this video for a while because to save the bandwidth. Okay.
Yeah. Okay, sir.
To see my screen?
Yes, sir. I can see.
Okay, perfect. Perfect. So thank you very much. Thank you, Satish, for inviting me over. And yeah, take a lot of time and effort from the team to organize such FDPs and CPs and STC programs. There's a lot of coordination and things are required. So all the best for all the upcoming sessions too.
Thank you, sir.
We'll go over look into visible light communication systems. So they are an alternative also communication system. They all fall under the same umbrella of optical also on the same umbrella optical networks, but here we use the our normal lighting infrastructure for communication as well. So what I'll try to do is give you a brief overview of what is what is visible light communication systems, and if there is time and scope left, we'll go into some of the applications of machine learning into visible light communication systems. But this technology has evolved over the years, and I'm not sure how many, if anybody has heard about visible light communication systems or LiFi, they can maybe raise their hand. Okay, so there's a few. Okay, there's a few 2 or 3 participants who have heard about this. Okay. Okay, so that's good. So that's usually a very low number, because not many has been working on it in India for some time. But it's good that at least there are 3 or 4 people who have been working or are acquainted with this technology. So because not many are, so I'll start from the very basic. So we'll look into the introduction. We'll look at some of the major companies in this. So this you see, this is not no longer like a sci-fi concept that this thing will come, maybe it'll be prioritized or not, but this is happening for visible light communication systems. So we look at some of the major companies working in this area, what kind of products are currently available. We don't see much in India at the moment, but we have some Indian players and partners working in this technology. We'll also look at some of the trials. So this has graduated from just being a concept to a product and deployments of those products in different places. Then we'll see what are the open issues. We'll see what are the solutions that can be. We'll look at a couple of them. There are others in the literature as well. We'll just go over some of them today. So visible light communication system. So this has emerged as a promising and green and also interference-free supplement to RF. So we don't say that it is a replacement for RF. It is a supplement to RF. So VLC relies on intensity modulation. So a simple example of a light-based communication system or working in the light bands, we can call it as we have been using our infrared remote controls for many years for controlling our air conditioners, our television DTH boxes, and also we've been using some form of communication using infrared. And infrared comes just around the visible light spectrum. If you look at this figure here, so we start from AM, FM, radar, infrared, and then we get the visible light, and after ultraviolet, and so on, X-rays and gamma rays. Now, visible light covers the wavelength from 380 to 750 nanometers. That's very huge, um, and that translates to 430 to 770 terahertz. So this is a huge bandwidth availability. And another advantage is it is non-licensed. So what does that mean? So like in wireless today, we use Wi-Fi at home, and we use cellular network when we are outside, or even at home as well. We use it, but generally the way it has evolved in the last 20 years is that we have been using Wi-Fi for indoor environments, be it offices, campus, or our home, which is a license-free um, uh, channels or bands. Whereas if I consider the cellular network, so they are licensed bands. What does that mean is for a telecom operator, if they have to transmit something onto in the air and they want to transmit a signal, they need to purchase a license, and that's what we hear in the news as well, that the licensing for 3G, 4G, and then now 5G is auction is now going on at the moment. So they will open up the tenders, and then they'll be putting in bids. Different operators will be putting in bids for good channels, of course, and then once they win it, then they'll put the deploy, and then they start charging. So as a user, if I have a SIM card, I'm a licensed user to that particular operator. Now, whereas for Wi-Fi, we don't need to purchase a license. We straight away connect it because it's transmitting in 2.4 gigahertz or 5 gigahertz bands, which are ISM bands, which can be used for industrial, scientific, and medicinal use. It's also being used in our microwave ovens working at the same 2.4. Bluetooth also uses the same band. So these bands are called as unlicensed or non-licensed band, where you don't have to purchase a license from the state to start transmitting. Reception is not a problem, but transmission is a problem. So you need to purchase a license for this. So here, for same thing for visible light. If I have to connect a bulb or a tube light, I don't have to purchase a license from the state. Right, I can straight away start switching it on and start transmitting. Okay, it is currently light, but future it can be used for. It is current, future is being used for data transmission as well. Now, another advantage is low cost and easy implementation since it utilizes existing LED infrastructure. So over the last, you see, about about a decade or so, we have seen a move away from incandescent lighting, so filament-based lighting, bulbs and tubes, to LED-based lighting infrastructure. So which is already happening. So if we can use the same infrastructure for communication, it is energy efficient and hence belongs to category of green. So it takes very less power as compared to an RF transmitter. And designing an RF transmitter for a MIMO or a massive MIMO is still a big challenge. Whereas for visible light, it is easy. I'll say if you open up, let's say, one of your um, LED bulbs, you will find a grid of 8, 10, or 12, or 16 LEDs. So they can be considered as uh, antennas in a MIMO setting. Now, well, that's very easy to install and then deploy. Same thing for visible light. If you want to do a proper, let's say, communication channel, it is easy to do. Whereas for RF chain, it is expensive. You need very expensive RF equipment to convert it, and also the power consumption is very huge. Whereas that's not the problem with LED lighting. Using LED for communication, it is also immune to interference from electromagnetic source while working in the light, in the photonics bands, not in the RF bands. So it is immune. And another advantage is that we have not seen many, equipments being available, for transmission in those bands. So there's not much interference there. Now it's highly secure, and a visible light is confined into a opaque boundary. Um, because the visible light doesn't, cross the opaque boundaries of walls, or doors or other features. It is secure inherently, right, because the signal is not going out. Whereas if you compare it with RF based communication system, so Wi-Fi, we see Wi-Fi in different, rooms and all. Even if you have a private Wi-Fi or private 5G network, still the RF is linked to other places. It radiates to other places, which can be, eavesdropped, as well. But whereas for visible light, it is not. So the maximum you will have is a window, and if somebody is trying to, eavesdrop from outside the window, you can see the person or the equipment right away, and still it is going to be attenuated quite a bit as it goes out of the window. But here in RF, there is a high possibility that you can connect through the walls. We do it at home and other places as well. So visible light is all communication is inherently secure than the RF based communication. So it provides a threefold goal of illumination, because for lighting we are using it anyways. Not like for RF we have to put up a different device which starts transmitting, and that is not used for any other purpose. Whereas for visible light communication system, we are using it for illumination, communication, and also for energy harvesting. What does that mean is we can use, and there are demonstrations available where we can use a solar panel which can collect the visible light communication signals that you are transmitting, and it will do energy harvesting and also communication at the same time. Also we can have photodiodes also, tuned to do energy harvesting and then doing the decoding. So it provides a threefold goal of illumination, communication, and energy harvesting. And another advantage, it provides high SNR due to high illumination levels. So as human beings, for reading, we go for high illumination levels provided by the LED. Hence the noise is low. Some of the applications are Li-Fi. We'll see them in the next few slides. Smart lighting. Um, um, so we have seen some places in some cities what they have done, put some special zones where, let's say if there is even a, they are being monitored, but let's say even if there is a small incident that has happened or happening, they can change the color of light. So it avoids any you see offense being created, because somebody is watching and person can get dissuaded by seeing the changing of the light based on their activity, right? So that is a deterrent, reconnect as deterrent. Again, safe for usage in RF sensitive areas like hospitals, aircrafts. I guess see, whenever we travel in plane, we are told to switch off, put the phones in airplane mode, and our smartphones, they have this mode. So that is for a reason that we should not be transmitting in RF during the takeoff or landing. Now this is one application where we're going to see soon the visible light in action. Also in chemical plants and other places or refineries where, let's say, RF is could pose a danger. So those are the places where visible light can be used. So it's not a replacement for RF. It will work in conjunction with RF communication system. intelligent transportation systems like vehicle to vehicle communication, vehicle to infrastructure communication systems, where let's say I have a vehicle which is behind a vehicle which is in the front. They can talk to each other, they can communicate their information. Or let's say you are standing in the um, let's say you're standing in the traffic signal, and then suddenly let's say you're standing, you're waiting for it. So the traffic lights, they can traffic signals, they can transmit some generic information. So that's also some of the things that people are trying. Then IoT based applications, here we are seeing some of the players in toy industry like Disney and others jumping in to provide use visible light in their toys. Another other various applications for smartwatch and others, we can use visible light communication systems. Wearables. So that's the next, as I said, smartwatch. This is the next, big thing, a big application where we see that visible light communication will take place. And this figure shows a bit of an overview of different applications there are. So you can see personal area network. This is the most common one, where we have a conference halls, we have different lighting. I'll show it in the later slides how it is physically done in different setups across the world. Transportation hubs, we can use in home and office. We can use lighting. um, then data showers, they can be, because we are having these lighting infrastructure, and different cities are trying to provide free Wi-Fi or some kind of connectivity, so they can use the lighting poles for as data showers. Intelligent transport systems, where vehicle to vehicle communication can take place. Vehicle to infrastructure, that can also happen through visible light. And then in the non-RF friendly environments like in mines, or EMI sensitive areas like hospitals, aircrafts, and other, for um, kids and all. If you want to keep them away from RF, then the security, anyways, because you're in an opaque boundary, it is not. Also, people are trying visible light in underwater communication systems. Um, then we have smart lighting for indoor. So there's another application here. I'll show later, which is for using positioning, and in a shopping mall it has been deployed with help from Philips. Augmented reality, again, because we get very high data rates, we can we're talking in terms of GPS, so very high, hundreds of Mbps download speed, so we can do AR VR type of applications. Entertainment, okay, of course, and then replacement for cables and smartphone applications. So smartphones can talk to each other, or in a very short range communication systems. So these are some of the major companies working in the area. So we have Pure Li-Fi. This is one of the biggest VLC companies, founded by Professor Harold Haas from again IDCOM, University of Edinburgh. He started this company. Um, this has been doing research and also product development over the last decade. Firefly Wireless Networks, again, based by Light Pointe, based in France, and then Oldecom, again a French telecom company working closely with University of Paris, Saclay. Then VLN Com, based out again from Virginia in the States, looking at visible light. There are other players as well, like Signify, Lumen, Lumi, for you'll see Philips, Wipro. So from India, we are seeing Wipro doing a lot of research activities. Cognizant as well doing a lot of research activities, development activities in this area. And what has happened over the years, we have seen the the lighting companies like Philips, Wipro, and all. They are moving into Li-Fi, because see, the lighting comes naturally to them. They understand the lighting infrastructure, how it has to be deployed in even in large industrial setting like airports, or stadiums, and big offices and all. So they understand this lighting very well. And when they moved away from incandescent bulbs, there was a need to move to LED. Now these LED bulbs, they are energy efficient, but they are also you know um, they don't go bad or faulty very quickly. So you will generally get a very high lifespan, sometimes 5 years, 8 years as well. So uh, these companies, they had a when the incandescent, the bulbs will go off, the Philips, you will go and buy another Philips one or Bajaj or some other company. But now this is not happening so frequently. So they wanted to look at alternative revenue streams. So this has come, you can say, as a savior for them. So there's a lot of lighting companies which are behind this, pushing this technology as well. Now, these are some of the products. We'll see what these are. Let's see this one, which you can get it. My Li-Fi as a desk lamp. So user can connect to the internet through optical fiber. So you can actually have optical fiber directly coming here for tabletop desk, or can convert it to. But this is a very simple design. If you see, it's a fiber that's coming across, and there's a data shower. So this can accommodate up to 7 connections. Um, and secured by again a single device, and can give you transmission of to 23 Mbps for downlink and uplink. Then you can have Li-Fi Max. So these are more like our lighting that we can put in our home in on the ceiling. So it's fast, secure connection, free from RF plug and play systems that can easily be installed in any room. It guarantees fast data transfers, 100 Mbps download and upload. So that's really huge. Compatible with any device, um, because we are using Windows, Linux, Mac, different operating system, Android. So it works with any of these and can use a or C type USB. So these are real products available in the market that can be purchased, and you can start your deployment, and can this can support up to 16 simultaneous users. The life I can. No, this slide just tells you that, yeah, in the hospitals and all, where at some places where RF is prohibited, where we can use visible light communication system. Now this is a dongle type of device developed by Pure Li-Fi. This is similar to the dongles we used to use a few years ago. So if I have to connect my laptop through to so nowadays, like most of us will probably be using like I'm using the hotspot from our cellular network. Um, Whereas in case of early, before that, before we had this hotspot, or even sometimes the hotspot is not so good, so we used to have a dongle, and we'll put the SIM in the dongle that will connect to the cellular network, and we can do browsing from our laptop. A similar concept extended to visible light, because currently there's no support in our laptops for visible light communication system. So we can use one of these dongles and can have this lighting. Let's say I have one of these lights, Limax, and then I have got this Li-Fi XC, which is again the first dongle. So it works again in different operating systems and can give you a download speed up to 42 Mbps. These are other applications. So this is by vehicle secure link. Again, this for infrastructure, vehicle to vehicle communication system. So this is being tried by many, so we'll see them in the initially in the high end cars, where they are putting, because we've seen in the vehicles as well, right? From two-wheelers to four-wheelers, all the lighting has been slowly replaced by LED lighting. So they can be used, you see, for communication purposes. Hello, is my voice clear? Somebody is saying that voice is not clear.
No, sir, it's very clear. I think they are having some network issues. Yeah.
Okay. Perfect. Okay. Yeah. So I just wanted to check. Yeah. Okay. Then office secure link, like you can have a secure office, because again the RF doesn't go. And yeah, okay, I'll say it later because there's another slide on that, so I'll go over. So this is, you can have this lighting like this at home, and put them in the ceiling. So this covers give you over 70 Mbps, and this covers an area of 400 square feet, which is good enough, for a decent size office or a shop. Can have one of these, and this can support 15 simultaneously. So it provides you lighting as well as your communication. Now, some trials, this is not exactly for visible light, but this is exploiting the similar technology for free space optics. So these were these trials done in Orkney Island, just off the coast of Scotland, so Scottish Islands, um, where an FSO front haul system with solar panels was used. Um, so this was so this actually map on the left hand side shows there is the mainland Scotland, then there's the Orkney Island. And then they connected these two through free space optics and used solar panel for doubling the speed. So this was like a small trial um, done in Orkney Island, which was having a very low support to a program called 5G Rural First, which was supported by Orkney Council, Cloud9, University of Edinburgh, and other Pure Life and other people coming together to show that this is a viable technology, just a prototype kind of thing, but it was able to increase the data rates to that small island. Then there is another one. So this is a previous one from Pure Li-Fi. Because again they're based in Scotland, so it tested it there. Then 6G flagship, they have a setup here, which is in this figure. And also, if you're interested, you can visit this YouTube link and can see how this actually works. So this is also a setup. If you want, you can either note it down or take a screenshot of this link. Right. Then this is yeah, this 6G flagship is hosted by University of Oulu. So first Kaz is using this setup to demonstrate that visible light can actually be used for lighting as well as for data transmission. Now Philips Li-Fi enabled this. So as I was telling you about, you can have a dongle. So you have a small tablet, have a dongle. It's pure from Pure Li-Fi. It connects to your Li-Fi light on the ceiling, and you can do communication there. So they have also been putting, so Philips has been putting this, has been trialing this in the real estate like company, Lacard, in the La Defense area of Paris. So they have been showing this, and it also works when there is natural lighting and user mobility. So the typical concern, if there is a sunlight which is coming into the room, then will it, and also will the user mobility have an issue? So it does communicate through, it does handle the both the ambient light, sunlight, and also the user mobility. This is an example done by Fraunhofer in Germany. So they put this in a small stadium. So this stadium is now this is like a classroom. This is done by in Stuttgart by Fraunhofer. So they also been looking at this prototyping of Li-Fi. Then there's another one in the Kyle Academy, again based on Scotland, where they use Li-Fi in the classroom. So you have a Pure Li-Fi and University of Edinburgh doing this small trial in one of the schools there. And if you have not met or seen Professor Haas before, so the first person on the right hand side who has this dongle in his hand, so he's Professor Harold Haas, the founder and CTO of Pure Li-Fi. So this plugs into a standard laptops, and you can start communicating. So as we used to do for our dongles for connecting to a cellular network. Right? We didn't need any much higher technology. Now this is another one which is done in Carrefour. Carrefour is like a big bazaar or Lions Fresh. So those it's a big supermarket where you can get products from different companies. So they have installed these through LED lightings from Philips. And you can use a mobile app to download the data. So there's a demonstration. You can look at it here in this link. So this will open up. If I click on, they will open up. May not have the, I don't know.
Philips has just completed the world's first major.
Are you able to hear this as well? or not?
Yes, sir. We can able to hear the video and as well as audio. Yeah, we can able to.
Installation of 2.5 kilometers of LED light features for Carrefour that contains patented LED-based indoor positioning technology.
So this hypermarket is the first hypermarket in the world where the Philips LED-based indoor positioning system is installed.
We work with Philips on energy savings, and we wanted to test a new service in Carrefour Lille and go beyond just lighting with using a new app for light. The focus we made is to just specify and localize the promotion for people.
Philips LED fixtures that are installed in the store use VLC technology, visible light communication. Each luminaire sends out a unique code that can be directly detected by any smart devices using a camera without any additional device or accessory.
Philips LED lighting acts like an indoor GPS. Each Philips LED light feature transmits a one-way location signal to a shopper's smartphone to trigger open an app that provides location-based services.
The main benefits for our customers through this new application is to prepare a shopping list with his promotion, and when he arrives in the store, he can localize all the product he chooses.
For Carrefour, this is the opportunity to offer location-based services that will enhance the shopping experience, making it more interactive and personalized.
But the lighting technology not only provides positioning, but also orientation and an incredible sub-meter accuracy.
So in this store, Philips LED lighting offer energy savings, quality of light, but also act as a real platform for indoor positioning. Philips LED lighting goes beyond illumination only.
So yeah, this was just a small digression, but just want to show this technology is working in practice as well, right? Hello, can you hear me? Hello. 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 Hello.
Sir, your voice is very low.
So this video some problem. Let me shall I reconnect?
We cannot hear you. Like it's very low actually.
Very low, is it? Okay. Remove this. Yeah. Okay. Now how
Yeah,
is it?
now it's audible, sir.
Perfect. Perfect. Yeah, there was some setting it did automatically. Yeah, I think it adjusted to the video. So
Yes,
yeah,
yes.
so, yeah. So this I just want to show that this is a technology which is not a sci-fi only. Live in the papers. It is coming to life as well, and we see light at the end of the tunnel. So we are seeing that these things are available, and people are using it for localization. And that's another very important thing in communication systems to be able to do effective localization. And with the and in the visible light in the light domain, when we're looking at terahertz, very high terahertz bands, here we are able to localize to very small fraction. So here this is used as you just saw in the video. They are using it, and the customers are using their smartphones, but they're using their cameras for see receiving the visible light communication system. Again, see, they're not looking at a very high speed download here, download speed, right? They're just looking at places where they can then interact with their with this Carrefour application. So we could have something similar, by big bazaars or others to put this. So this helps in saving the energy, and also helps in communication. So so these are all the also the good things about visible light communication system. So now let's see what are the other issues that are still challenging it, and that's where we as researchers come in to solve this problem. So now the LED channel, they have high impairments, there's a LED nonlinearity. So we know that the silicon devices, an LED, as a silicon device, it has a nonlinear, structure, transfer function. So it is affecting, the you see the this communication system, because our most of our systems we assume it to be in the you know uh, working in the linear region, but LEDs are, and also similar thing for photodiodes and the solar panels. So there is this limitation, right? So now uh, the intersymbol interference. This is something which we have been seeing it as a uh, uh, you see in communication systems, because we know we're trying to transmit a very high speed, and we're looking on on a limited bandwidth. We get ISI and other type of distortions. So we need to mitigate this at the receiver transmitter. Some kind of combination can be developed. Then user mobility. Now, because of mobility, this leads to multiplicative fading distortion and degrades the VLC link due to outages and non-Gaussian distortion. And then there's a DC bias term due to, so this is DC bias. Usually we don't see it in the RF world, but here we have to, because again, if you're trying to transmit a complex signal or a constellation which has a negative value, we need to push it into the positive region. So we use a DC bias, and this can cause the decision boundaries to change. So this also needs to be handled well. uh, no, the VLC channel impairments, if these are all there, and they are all there in physical world implementation, so we have significant degradation in the achievable beta rate. This causes significant performance gaps between the promise and the achievable throughput. So theoretically, we can say, let's say, you get a BR of 10 to the power minus 6, but in practice you may get 10 to the power 4, 1 to minus 3. So why this is happening? Because of some of these reasons that we know of. The throughput of existing VL system can be increased by using a massive MIMO setup. We have been, as I told you, it's easier to set this up in visible light, but then there are other pitfalls. Uh, if you do this, then there is a ill conditioning of massive MIMO channel. So this increases as the number of LEDs and photodiodes per unit area increases, which has the issue with the spatial channel being correlated. So they're not you see, independent of each other. So we are not per se getting the whole, all the channels as independent. So this is one problem. So this is ill conditioning. So it is actually ILL. It looks like 3, but it's ILL. So the first word is actually capital. So, and the others are small case. So the inversion of a ill conditioned channel matrix then results in noise amplification, which degrades the overall performance. Similar to you see, if you are using a MIMO receiver, you're using a zero forcing, it will amplify the noise. Similar thing here as well. So what are the solutions? So solution in a typical communication from a basement engineer perspective is, you can use a pre-distorter or a post-distorter. Now pre-distorter you can use at the transmitter, this and the post-distorters are used at the receiver, or they're also called as equalizers, right? Now let us see what solutions have people been proposing over the years. So there people have been using a very simple implementation. So we have a lookup table, very elegant solution, very simple, which basically stores the IO pairs for the nonlinearity of LED. So if you are LED manufacturer, if you publish your data sheets and gives that the LED has this characteristics on when we change the input voltage, the change in the so it'll be linear, and then there's a nonlinear behavior. So if I am designing a pre-distorter, I can do an inverse of it at the transmitter itself by using a lookup table, pre-calculated values of the inversion, and then pass my signal through it, right? But it's not suitable for modeling dynamic nonlinearity, because this is a fixed solution, right? It's a fixed for one particular um, LED. Now, if over the time or the sensor channel changes, Oh, there are other things that come in. So this then there's a dynamicity. It is not exactly the same, maybe because the temperature changes, the humidity, the LED characteristics changes. So those things cannot be modeled. And then the another problem is, let's say tomorrow you have to replace a photodiode, or let's say you have to replace the LED itself. Then your lookup table needs to be updated too. So that is a very static solution, very elegant, simple, works very well. But in practice, it's a limitation because there's dynamicity in the system. Now, K-Metal, they propose adaptive linear normalized least mean square. So least mean squares is an algorithm that we would use for channel estimation or equalization or system identification. So there's a lot of other applications for this. Very simple algorithm known for last 40, 50 years. Works very well. So they modified that for tracking the nonlinear response of LED. It delivers a suboptimal performance for LED characteristics because again the LED characteristics are non-linear. So when we propose a solution, we consider the nonlinear behavior of an LED and propose a relative nonlinear Chebyshev. So very one of our very first works, very interesting work. If you have a chance, please go over. It's a small 4 or 5 page letters, but it's a very elegant solution where we use a nonlinear structure of the filter, Chebyshev filter, and updated the ways using NLMS. But there was limitations in this one, relies on the perfect feedback of detected symbols at the transmitter. Um, now, however, because the pre-distorts, they rely on the perfect feedback detected symbols as a transmitter, which poses a problem for this. So hence, working on post distorter is required, even if you're working on pre-distorters. That means you have to work on the equalizer type of algorithms to help the pre-distorters work. But or some channel estimation, something has to be done at the receiver, which will be sent back to the transmitter to design a pre-distorter. So in the post starter, again, there are again 2 or 3 groups in the world who have been working on this. So Stefanik, they went for Volterra DFE. So Volterra DFE is a type of equalizer, Volterra decision feedback equalizer, in a very classical solution using polynomial series expansion of a nonlinear function. And it is one of the, let's say for the linear case, if I use LMS, for nonlinear I'll use Volterra. It's like a de facto uh, um algorithm that you will definitely try against, and it is still being used very popularly, also using optical communication. We're using fiber um, for communication links, so that's where it is also used. So they use Volterra and Hammerstein based polynomial expansion. It has a high computational complex and also modeling error because we are always limited by how many polynomials we want to choose. So our work has been a bit different. We're using RHS based techniques. So this delivers suboptimal performance over highly compressed this, but the advantage by using kernel LMS, we made it a, a nonlinear handling easier, and working in RHS is we'll see a little bit in detail later. Then now you might be, some of you might be conversant in neural networks. So Gazamgloy group based in Newcastle in the UK, they have been working on using ANN or Gaussian kernel based equalizers, where again their limitation is it's non-convex. Then solution becomes difficult, computationally complex, and it's highly sensitive to choice of hyperparameters. Whereas RHS based techniques will guarantee a convex solution. It is computationally less complex. With some tricks we can do it. I'll show later. And it is also it's sensitive to hyperparameters, but then there are some solutions, recent solutions, which makes it independent of the choice of the hyper parameters. So here, let's look at this. So here, there's just one thing. I'll just recap. So this LMS is there, least mean squared. Now there's a MSER. So this is called as a minimum symbol error rate criteria rate. Because from the equalizer point of view, equalizer used as a receiver, the performance metric, how we test the performance of an equalizer is through bit error rate measurement, right? So then the question arises, then why should I have, you know, um, squared of the error as the criteria for an equalizer? And that's where we have been working for last couple of years on last about 2 decades actually last about 2 decades working on this MSCR criteria to be able to adapt the systems using this MSCR criteria instead of the minimum mean squared error, which works far better than MSCR criteria in a regions where the noise is either non-Gaussian or there's no linearity in the system. Now, RHS-based post-disorders are found to outperform classical because, as I said, polynomial series-based one, because the RHS one provides us convexity as universal approximation is provided and low computational complexity is achieved by sparsification. We'll see, just briefly touch base on one of these in the interest of time, but it gives you just an idea. You can apply it in other domains as well, or maybe it has already been applied in other places as well. Um, but then there are certain issues we found with the feed forward RKHS one that it provides a suboptimal performance for multipath VLC channels, impaired by high intersymbol interference non-Gaussian noise. So what we proposed was a modification of the distance feedback equalizer because they are DFE, as I said, no, that is very Volterra based DFE, but DFE is a very common architecture for handling um nonlinearity or even linear ISI as well. It works far better than other algorithms. So same thing we used here because DFE decision feedback equalizer has a feedback uh, mechanism, right? So this is something we'll go over. Now further, non MSC credit like MSC as we already discussed is a stronger one, and RFF is something that helps us to make it even better. The architecture technique again we'll probably not be able to go over, but just wanted to give you a small overview of where this adaptive signal processing or machine learning type algorithms are heading towards. Now we'll go a little bit deep into this problem. So here we have um, um, a communication system where LED has nonlinearity. I have a L-conditioned massive MIMO channel, and there are DC fluctuations. Now, what should be my approach? What we have proposed is using a hybrid adaptive precoder and pose. So we are doing both precoding and pose. So doing equalization and versus precoding. There's some kind of feedback mechanism that shares that information. Now, to mitigate LED nonlinearity and reduce condition number of overall channel matrix, this contribution proposes joint RHS based adaptive MSCR recording and pose structure for massive MIMO. You can go in detail in this publication here. I should note it down. Now this is a block diagram. I have a Capcom modulation scheme. It goes to a pre-coder. Um, you can think of, yeah, I think in later slides it will be given, but these you can think of as some weights which are calculated. So precoder has some weights which will get multiplied with xk. Then there's a DC offset. How we calculate this weight we'll see later. Then there's a small DC offset so that we are only in the first quadrant, only using the positive um, you know uh, voltages. Then we have a LED array. So F is an array function. So F will introduce some kind of a nonlinearity in the system. Then we have a massive MIMO channel given by capital this H, bold H. And as we do typical in the baseband processing, we have AWG noise, which is given by NK. Then we have photodiode array, YK, going through this, inversion of this channel, or basically, so these are like expansion, and actually the SVD expansion polynomials. So we'll basically do a pseudo inverse and multiply by yk, we get y dash k, and this y dash k is then put through the post distorter, and then we have a KMSCR criteria here, which will update the received symbol and also the recorder. Now this is a training based system. What does a training based means, or in machine learning we call it supervised based learning, where a known set of input symbol is first sent. The system is trained on that, or in supervised learning, that's what we do. In machine learning, we'll send some symbols and it'll learn the system through that, and then after that the data is actually pass through. So here, if I were to, let's say, compare with machine learning, I'll say supervised learning. This is a supervised learning based one, and then I'll pass the testing sequence later on to find out my actual bit error rate when I'm going to transmit the data. Now let's see how the system model looks like. So that XK with the Capcom constellation, transmitted symbol vector goes through the precoder. Uh, we're given this web matrix P, so P times XK plus this DC bias. It goes through F. F is a nonlinearity introduced in the system. YK is what is received at the received photodiode at the kth instead of time, because it's an adaptive system and it's working in different time slots. So it is this we get NK is a thermal noise and NK ambient noise. So NT denotes the number of LEDs and NR denotes number of photodiodes. Thermal noise is modeled as IID AWGN. Ambient light is modeled as chi-square, but given a large degree of freedom, we can model it again as a rectified Gaussian noise. So combined, they can be modeled as a rectified Gaussian noise. And B is the DC bias factor, which is put the LED in the forward bias. Now, F, as I said, is a what we mod as a LED nonlinearity, which we model it as a wrap nonlinearity, given by this equation. Xk min VTH, Xk and VT divided by V max to Q. So this the value of this Q determines the level of nonlinearity. We can change this parameter. Again, if you want to find out exactly what values we have chosen, you can look at the our reference papers. You can see what values are typically chosen. So if it is above a certain threshold, then we get this nonlinearity. Otherwise, this results in zero. So it has to be above this. So that's what the this DC bias is added, so that XK is in the forward bias region. Now the channel is modeled like this here, where we have a channel matrix H, which has I and J are the impulse responses. I jth LED going to the ith photodiode. So Hij can be given by AE P plus 1 over 2 pi d I square Ij cos P raised to power P alpha cos beta, and then the rectangular pulse of a certain width. So alpha denotes the angle of emergence, and then beta represents the angle of incidence to the receiver, because they'll be at a certain angle for this for the visible light, and P is the Lambert's mode, or alpha half is the transmitter semi-angle. This again based on the geometry of the LED and the photodiode. Now A denotes effective collection area of the detector, and Dij denotes the distance between the jth LED and the ith photodiode. Phi is the field of view, because again that's also important for visible light communication system. Because if something is beyond field of view, then it's of no it's not going to be used. Uh, and then this denotes rectangular pulse for this. So basically, equation number 3 is telling us how the different channel components of the matrix are found. So here in the solution, we can expand this and SVD decomposing for the channel. I said U lambda V. So U and V are the left and the right singular vectors of H, and lambda is the diagonal matrix which has certain values. So or in eigenvalue decomposition, we can call it as a um, shear decomposition for this lambda weights. Now, precoder matrix is designed as P is equal to V is lambda K minus 1. So these are the weights that will be updating. So lambda is between 0 and 1 is the precoding index at the kth instance. We'll be updating these values. So let us now expand based on this expansion. Here for H and for P, we will expand what we received in Y. Here, right? Where was it? Yeah, just before this. Yeah, so Y equation number this one. So this will now expand and rearrange. Okay, now we are expanding this. So we assume that okay, the DC bias is perfectly cancelled. So I'll subtract the DC bias applying the Bose-Einstein theorem. We can rewrite equation as this here. Einstein f px plus b and k and ambient overall additive distortion. So this is uncorrelated distortion noise with zero mean and covariance matrices. Alpha is the scaling correlation and delta b is the DC bias. So DC bias erratum is modeled as a uniformly distributed between minus alpha, epsilon and epsilon, where epsilon is the variation range. Now the effective channel matrix can be observed. So we try to, so we can, yeah, maybe skip this one for now. We'll just look at the adaptation. So lambda k is optimized to using MSA criteria. So we have our objective is to, so these are weights. So these you can, so these are weights in RKHS, but you can think of it as weights of an, let's say, an FIR filter. So you have a previous value and then the current value. So you do a subtraction of it and then do squares. You find the mean squared error one, and this is so. But these are not exactly the channel weights. These are the weights in the RKHS, um, such that GK is another constraint. So GK is for an MSA criteria for QAM constellation. QAM is given in this reference number 15, is given by tan hyperbolic function for imaginary and the real part. So beta is a constant high enough to approximate a signum function, and lambda and delta lambda k is given by this equation. So now if I am going to change the modulation scheme here from QAM to something else, then I will have to change this function g of x. So this is something we need to we need to take care of, right? Okay, so this provides us this MSC. Otherwise, we could have used it straight away, MSC criteria. This again. So now, if you look at this update equation, right, this is similar to the. You see, this is similar to the LMS, or I can in general I can call it as um, a stochastic subgradient method, where lambda k plus 1 is lambda k minus mu k, and the first order derivative of the cost function here, which has the weights in the RKHS. This the second part g lambda k. This covers the MSCR function, and with some Lagrangian multiplier, I'll come here and then in onto this in the Hermitian in the Hilbert space. Sorry, Hilbert space. Now here we calculate the gradient by taking the first order derivative. I can expand it and then place it. So basically, what I want you to take away is that yes, we can update lambda k using MSCR criteria, and then the weights can also be updated using the MSCR criteria. Now, if you're interested to go in detail, you can look at the paper. So basically, what we're going to do is doing adaptation, and because we're using a kernel, so kernel has a certain width. We have to, or you can fix up a constant value as well, but that's not may not give you an optimum solution, or not the best results that you're looking at. So you can also update the variance parameter, but that is again, I'll say, optional. You can start when, let's say, your first time implementing it, just simply make it a constant value and then try it out. Um, and then you can apply this. So now there is one criteria called a sparse criteria. No, with machine learning and RKS-based solution, what we tend to do is when we are learning, we will store a solution in a dictionary. We'll start to build a dictionary of certain solutions, and given a point, we can then you know in theory I need infinite memory size, but then in practice we don't have infinite memory. So again, as I said, in theory they work very well, but then in practice we are limited by the compute and the memory requirements. So here, if we do some kind of sparsification, and this is what the criteria is looking at. If let's say we say that the phi yk or phi dk, if they are already existing and their values, let's say, going to be smaller than some parameter I have taken as tau one. This values is a tunable values. So here we'll add it to dictionary. Otherwise, we can skip it from the dictionary as well. Right, so they are these parameters values that can be added in. So we are selectively adding things into the dictionary. So if let's say the value is very close to what there's some value which is already existing there, we don't need to add. So that's that procedure is called as sparsification. There are various algorithms, but we have been choosing is the simplest way of doing it. And what I'll just quickly, in the interest of time, I'll just quickly go over the setup that we have used in simulation. We have taken distance between two LED neighboring is 5.8 and 5.8 centimeter for photodiodes of LED. Effective aperture area of 1 centimeter uh, square. Um, then field of view is about 10 degrees, 10 degrees in both the cases. Distance between the transmitter receiver plane of 2 meters. Center LED array of 11.6, 11.6.5 meter. Photodiode are 36 and array of 16. So two of three of these configurations we have chosen to see the impact. Again, 16 Capcom modulation was used over 10 to the power 6 symbols. And there's some of the parameter values that we have chosen. You can again look at it in details in the paper. But basically, I just want to show that by using the proposed techniques, we get a significant increase in the performance. For example, if you look at this graph here for proposed precoder linear LD, we get this because it's linear. But again, if I put the nonlinearity, then again the performance will degrade a little bit. But by using the proposed technique, we can still get better performance. And the right hand side one is showing number of iteration versus dictionary size. So if let's say I'm limited by the compute or limited by the memory, I can say, let's say if I can only afford 300 or even 200 memory size, then I can go for one of these other algorithms than the one that we are. So we have different choice to choose from. So from a system, developer point of view, if I have know both, it helps me in designing my relative hardware. It's a similar performance we've seen in others as well. Um, Nothing we can maybe so in interest. I mean, if there's any, so this is another architecture where I was showing the decision feedback equalizer. The feed forward, and there's some feedback which is back. Now we have modified this to work in the RKHS plane, and that works very well again in handling the nonlinearities. Then this can be done in this can be done through you see um, a blind type of equalization or unsupervised learning as well, where we can you see go through so in this slide it's not there, but basically we can do both supervised and unsupervised learning both uh, for this. So actually in the interest of time, if there's any questions on it, we can because I have actually another appointment just soon after, so maybe I can stop. If there's any questions or queries, you can either email me or ask right now. That is fine. That's okay with me. Some of the future direction work that you can look at, making them hyperparameter free or random receiver orientation, mobility. That is also because you see when I'm at home, handset.
Hello, sir. Can you hear me?
Yes.
Sir, can we take few questions, or sir, you are getting late, sir?
I can take a couple of questions.
Okay, sir. Sir, you ask, please.
Sir, good afternoon. So it was a very informative talk. Thanks for that. I have just some generic questions related to the visible light communications or Li-Fi in particular. So what do you think the challenges the industry is facing to implement this Li-Fi technology in a very large scale? But you have showed us like some implementations in your presentation, but we cannot able to see this Li-Fi in a very large scale actually. So what are the challenges that industry are facing?
Yeah, so this is so there will take some time to come. You see, from concept to this stage, also it took a while to come over. But this is something that will come, and also once the devices are more devices are available, we can see more of these will come. So I mean, I'll say it is a matter of time that more devices. So again, see, the initial ones will be more expensive as well. So once it gets more commoditized, then things will happen. So I mean, these were just to show that yeah, it is coming. So once let's say there are more customers on board, because again, our mindset also, looking at Wi-Fi, why should I put a Wi-Fi infrastructure in my home when I already have a Wi-Fi? Because there'll be some cost involved, right, at the end of the day. But let's say if I'm convinced that yeah, I have to live in a RF-free environment for health reasons or others, then maybe I'll go for this energy reason. So whatever reasons I'll go for it. So same thing happened with LED lighting. So that has been there, but then there was a push, and then there was a push from the government as well, giving subsidies and other things so that people move away from incandescent, saving energy. So if that kind of push comes in, then of course, otherwise yeah, I think industry will takes on time. But it is something which is we have an alternative Wi-Fi, so that's another I'll say a barrier, entry barrier. If there was no Wi-Fi, then this would have really kicked off.
Yes, sir, I agree to it. Yes. Sir, one more question from the participant. Uh, yeah, so kindly explain the parameters that will vary due to this VLC, visible light communication, like due to time varying VLC channel. The parameters that needs, I think the question is the parameters that needs to be considered for visible light communication, like some of the parameters that can be considered. Yeah.
Just for the setup, there are, say, let me just go back to the slide. So for the setup, there is, so for algorithm, there are other parameters, but for the, just for the setup, well, let's say you are agnostic to the type of algorithm or solution you want to implement. So I covered a few, right, where there was things were mentioned. Just going back to that slide. So these are some of them. And again, if you let's say want a detailed one, you can visit one of our research papers and see
Okay, sir.
more detail.
Yes, sir. Yeah. Yeah. So over to Dr. Satish.
Yeah. Sir, I have just a small question. Just I want to know because it's new to me. Sir, is this VLC a line of sight communication? And if yes, then how to optimally choose the number of light emitting sources?
Yeah, so that's a good question. Yes, it is primarily a line of sight type of communication systems, but again, we do get light in other corners as well, or there could be some other configurations. But yeah, primarily it is a line of sight type of communication channel.
Okay.
And
So, yes, sir, I mean, there is scope for optimization. Yeah. Thank you, sir. So, thank you, sir, for accepting our invitation. It was indeed an informative and wonderful talk on visual light communication. I think your talk will be very beneficial for our participants. I once again thank you, sir, for your wonderful talk. Thank you very much, sir.
Yeah. Sorry, I actually have another appointment, so I need to rush. But
Ah, yes, sir. You already told me, sir. Yeah. Yes, sir. Thank you, sir.
email me any queries. Yeah.
Oh,
Thank
okay, sir.
you, your team.
Thank you.
Thank you, sir.
Future talks as well.
Okay. Thank you, sir.
Thank you. Bye.
Okay, dear participants, there is going to be a session at 3:30. So we'll be having a 20 minutes break. And then there will be another session which will be delivered by Professor S.K. Patra, Director, IIIT Vadodara. So that session will start at 3:30 p.m. for your information. So thank you. And so we'll be joining again at 3:25. Yeah, thank you very much.
Yeah, good afternoon, sir. Sir, can you hear me?
Audio is not connected. SARS audio not used.
Okay. Then we will wait for another 5 minutes.
Yeah. Sir, your audio is not connected. Please look into that.
Am I muted? No, you are muted. Sir, can you hear me? Good afternoon, sir. Sorry, mute me.
Okay.
Good afternoon, sir.
Hi, good afternoon.
Uh, so shall we start? Okay.
Yeah.
So good afternoon. I, Dr. Satish Tiwari, welcome you all to the second session of day 1 of our FDP on recent advancements in optical communication and wireless networks, organized by the Department of EC, SRM University, AP. In this session, Professor S.K. Patra will deliver a talk on deep learning for wireless communication. Professor Sarath Kumar Patra received the PhD degree in electrical engineering from the University of Edinburgh, UK in 1998. From 1986 to 1989, he was the scientist B at DRDO. Since 1989, he has been associated with the Department of Electronics and Communication Engineering, NIT Rourkela, where he is currently a professor from 2017 to till date. He is serving as the director of Indian Institute of Information Technology, Vadodara. He has successfully He has successfully executed several research and consultancy projects at NIT Rourkela in the field of communication and signal processing. He has vast experience of guiding PG and PhD students and has numerous publications in the broad area of communication and signal processing. He is the member of various societies and a senior member of IEEE. I request sir to please take over and start your presentation, sir.
Can you hear me?
Yes, sir, we can hear you, sir.
Okay, thank you. Just a minute. Okay, let me share my screen so that I can share the presentation.
Okay, sir.
Are you able to see my screen?
Yes, sir, we can see you, your screen, sir.
Okay, fine. Let me open my presentation. Oh, vanished. Yeah, is the screen visible now?
Yes, sir, it's visible, sir.
Okay, thank you very much. Good afternoon to you all. In this summer, I hope I will be able to keep you all alive in this session and keep you active at the end of the session. Well, the broad topic is primarily machine learning for wireless communication, but I go with I've given a specific title, which is deep learning for wireless communication. Now, what I intend to do in this talk is cover quite a bit of things. I would start with the wireless communication in general, and then move towards different evolutions of wireless communication generations, look a bit into machine learning, and we'll also look at few applications where machine learning has been used as wireless communication systems. How much time I have for this? Hello?
Yes, sir. You can continue till 5, sir.
Okay, that's about 1.5 hours. That's fine.
Including question and answer session, sir. We have time till
That's fine.
5 p.m.
Okay, no problem. Okay. So now, if you look at the world, what the world went through was different forms of communication. Now, I was born in 60s, and being born in 60s gave us an opportunity to see a wide variety of communication technologies in the world. I consider myself to be lucky in that aspect. Before 60s, communication was very primitive. The technology reach was very, very low. And the India being a third world country at that time, a country belonging to third world, had a lot of difficulties in adaptation of technology due to the cost. Now, if we go back in historical time, the first thing that happened was, if you look at the modern world or world after 60s or 50s, first thing requirement was to go for a communication where people could talk to each other or could send some messages to others. Now, initial technologies were such, they primarily supported voice communication. Support of audio was very low, and video was almost unthinkable. This continued till 70s, and in India, it was even the condition till 80s. Gradually, the demand for transmitting or sending or communication using images, videos, and multimedia started to come up after that. In fact, I remember 1986, there was a World Cup. And that was the first time when we got a chance to see World Cup football match in color. Not only that, before that, 1982, India had hosted the Asian Games. And that was the time when color television transmission started in India. That was the time when color transmission in terms of video transmission started in India. India had some amount of video broadcast, very little before that, but it was very, very little. And only a few cities in the country had that facility. And I had a chance to use that during my initial days at my engineering college, when I was reading in my engineering college. So if we go back to history, there has been a demand to send images, videos, and multimedia, but then technologically, it was not possible to send them out. The reason was the technology was not ripe at that time. Recording was tough, digital world was not developed, and majority of the things, or rather almost everything that we do that was done during that time was with analog technologies. Look at this page. This page shows the electromagnetic spectrum. It starts with very, very low frequencies, where the frequency is about 3 Hz to start with, and it goes up to 30 exahertz or even going up to 300 exahertz. Now, if we look at 3 Hz, the wavelength is very, very large. And with time, we have moved from left-hand side of the scale to the right-hand side of the scale for communication purpose. Of course, as far as technology is concerned, we had X-rays being used, gamma rays being used as old as 30, 40, 50, or even 60 years back. Even thermal cameras were used long back. But when you look at communication technologies, the communication technology usage came up very late. When I was a school student, I remember listening to radio. And these radios typically operated in the medium and shortwave band. And that band was typically below 30 megahertz. typically below 30 megahertz. But then when I was in my undergraduate, we started to get television, and it was around few hundreds of megahertz. But then a time came when satellites were launched, and then satellite communication started. And the satellite communications worked at around 3 gigahertz, 3, 4, 5, also towards 1, 1.5, and all that. Then gradually what happened? The requirement of higher bandwidth to send out superior information took over, and then everyone, or there was a requirement to go to higher frequencies so that one could use better bandwidth and superior technologies for communication. Now, today, majority of our communication for long distance and high information content is done at gigahertz level. Remember, if we move to higher end frequencies, we will be able to send more information because it would have a power to carry more information because of the available bandwidth. Now let's look at some of the frequencies which are very popularly used. Now, many of you who are attending this course might not have used majority of these frequencies. First thing, if you look at it, the lower side of it, you see the SIP, that's the very low frequency. In fact, in 60s and 70s, that was the de facto standard for SIPs to communicate with the shore. As this frequency was such where the communication was possible over a long distance. Then came the low frequency signals where the wavelength was between 1 kilometer to 10 kilometers. Remember, this is also a very low frequency. Bandwidths, the wavelengths were large. There were difficulty in transmission, both of these frequencies. Then came the medium wave and short wave. The medium wave and the short wave frequencies primarily helped in the sense that they made the radio communication feasible. Now, the sizes of the antennas reduced. We had commercial broadcasting by governments, commercial broadcasting by different agencies across the world, and thereby a communication method throughout the world was possible. Shortwave radios could be transmitted from one point to shipped throughout the world, and these things started. It was around in India, it was around 1980s or 81, 82, 83 like that time when television transmission using VHF technology started, and FM transmission also started around the same time. It was also the time when the satellite communication started. The satellites used centimeter wavelength, and then they could provide a large coverage over the land. The use of still higher frequencies for different communications came up after that. Now, if we come to the world of communication today we are using, or we are accustomed to use, what is called 4G communication. Now, the 4G communication, if we look at it, it uses different sets of frequencies, and these frequencies use different methods of multiplexing and multiple access. And there are some parts where frequency division duplex is used, and in some places time division duplex is used, and there are bands allotted for the standards. Now, we don't spend much time on this. It will come up maybe later. Now, let's look at how the cellular networks and cellular communication evolved over time. How the cellular network and cellular communication evolved over time. Now, it was around 1980s, later part of 1980s, when the first cellular network started. Now, before the cellular network started also, we had some amount of mobile communication in terms of phones. Remember, earlier, before 60s, before 80s and 90s, whenever a communication was thought of, it was always directed towards voice communication. Data communication was impossible, scanning never existed, and communicating with mails and messages were non-existent. So the communication at that time was primarily a method by which people could send information from one point to the other with voice messages. some amount of telex and telegram processes also had started. Now it was the 80s when 1G started. Now this 1G referred to cellular networks, or where it is truly mobile communication. You could hold a telephone handset, move around a city, and still talk to people. Very, very expensive at that time. The handsets were huge in size. Battery consumption were awfully high. The whole technology worked on analog techniques. This continued, and it was in 92, towards the later part of 90s rather, it was 1992 when the 2G got introduced. Remember, 1G was only for voice, 2G started for voice. Now 1992 2G got introduced, and at that time the 2G was very, very expensive. Even 1G and 2G coexisted till towards late 1990s. 1998, 97, 98, they existed together. I remember during 1998, I have seen the 1G telephone handsets being sold in the street for a very, very low price. Things like 10 pounds to 20 pounds a piece. That time they were sold cheap because 1G was about to end, 2G was already in the market, and 1G was getting obsolete. So the companies started to sell out their 1G phones at throwaway prices. But then after 98, things started to change very, very fast. In fact, many people of my age would have used a handset or a telephone set or a mobile cellular phone of 2G type. Not many of us have used a 3G network truly. That's whole of India almost. The 2004 came with 3G networks, and the 3G network brought in what we call is a different experience. It was designed for higher data rates, some amount of video capability, at least images and characters to support email and things like that. The technology wise, it was full digital. 2G as a technology started as a analog plus digital. 2G was analog plus digital. 1G was completely analog, and 3G became completely digital. So we moved from analog to digital in this move. 3G didn't stay for long in our country, at least. Around 2012, we had the 4G. As soon as it got launched in the world, India got it, thanks to the Reliance India Mobile. And then we got the Jio connection, Jio One. They were the first to start 4G in the country. And when they started 4G, other companies were working with 3G. And then the whole technology started to move and change. Very interestingly, you will find we are at the beginning of 5G. And what's interesting is with 5G, the technologies are changing. There are trials and commercializations. Now, if you look at the trial and commercialization, it was a few days back, I think it was last week, when IIT Madras demonstrated the 5G network and the indigenous 5G network. And it was done, and there is a lot of news on this. This is the news of last week. And what the world is looking forward to is going towards 6G and beyond by 2030. Remember, 5G we are expecting now. Maybe in next 1 year, it will be fully in the market. The commodities will become cheap. Mobile handset will become cheap. But by 2030, we expect that the 6G would be coming into the market, and it will be available for us commercially. Now, remember what we are looking at in 5G is machine type communication. That means you expect machines to communicate, and lot of mobile broadband with respect to data transmission. Now, these two things will certainly drive 5G strongly. Now, having gone there, having discussed that, let's see a bit about the history, how the cellular networks and wireless communication technologies came up and started. You'll see interestingly, the communication, if you look at, it started somewhere around when you look at the 1G system, primarily what we see is you have cells in a region, a geographical region is distributed into cells, and these cells work or help to what you call is permit people to move and talk. The possibility of using the communication device over a range of areas without losing out on the energy storage is the one. The technology that it uses is the same. But 1G had lot of demerits: poor voice quality, poor battery life, large size phones, hardly anything of security, call drops, and limited capacity. You can see here the type of handset that was used and that was available at that time. Now, this stays for a long time, but then this is a technology that was used only by the advanced countries or economically rich countries. Japan, Europe, USA used it frequently. India hardly had it. India, to my best of my understanding, India never had a 1G network. Now, India had the 2G network. Now, let's look at one part. I think every one of us have heard about what's called Moore's law or Moore's law. Now, this law is associated with computers, where it is said every 13 months, the cost of the chips become half, and the packing density or number of transistors in a chip gets doubled. Very similarly, it says that the cost of data transmission also would become half every 12 or 13 months. That has become now 2 years. And the cost of the hardware also would go down with time. Now, this is again related to silicon technology, which has changed it. We have reached almost a threshold of size of the chips, size of the transistors or the building block of chips and all that. But nevertheless, you can see from 1990, when we were looking at a data rate with wireless LAN, we were looking at a data rate of about 1 megabits per second. And with cellular, we were looking at data rates of fractional kilobits per second. We have moved to a time where in wireless LAN, we are looking at gigabits per second of data rates. And in cellular networks, we are looking at speeds or data rates to the tune of megabits or tens and hundreds of megabits per second. With time, things have changed so much. And we expect a lot more to happen with 5G and other technologies. And if you look at the wireless LAN, it started with 802.11b, then came G. In between, we had the 11A. Somewhere here, we had 802.11a. We got, then after G, we got N and AC. Now remember, as we moved up, it is today with wireless LAN, we are able to achieve multiple Gbps of data links available from a wireless network. And we could access that data either using a tab, a mobile phone, or a gadget, or a laptop, or a computer, or a mobile computing device, and whatnot. These technologies, maybe around 15 years back, were not available. The data rates were very low. Communication took very, very long time. Now look at 5G. We are looking at a 5G as a technology. 5G, what it envisages is, it is supposed to be a fully packet switch network. Where it started with 1G. 1G was a complete circuit switch network where when you call somebody to speak, you create a path which is a circuit path from the speaker to the between the two endpoints, that is between the two entities of the communication. But gradually things have moved from a circuit switch network to a packet switch network, where the resources of the physical layer are not reserved for one user. And in a packet system, the resources are shared by multiple users, and data is sent in packets, and any data or any form of information is converted to data to be sent. What 5G looks at is a flexible channel bandwidth between 5 to 20 megahertz, which says if I have a HD movie to be sent out to my friend or to receive a HD movie over my cable, I would get a different type of data rate. But if I'm talking to somebody, I will have a different type of data rate. And data rates to the tune of at least 1 Gbps is feasible. Now, when we were looking at 1G, 3G, we were looking at 1 megabits per second. But 5G looks at something like reaching a target of 1 Gbps with wireless technologies. Remember, with Ethernet, it's easy. Ethernet has gone up to 40 gigabits per second and 100 gigabits per second. But wireless, 1 megabits or tens of megabits were difficult. Now Gbps has been achieved, and we are looking at Gbps data for individual users at their home. Few other characteristics of 5G. One is everyone, everywhere, and always connected. You expect anybody to be connected, always connected, and wherever you move, you are connected. And then you get virtually infinite data rate. That means you feel that the data rate or the communication link available to a user is infinity, which means it's a perception that the user gets that they have infinite data available for their use. Going up with the objectives. With respect to 4G, what the objectives are looked at is, you are looking at thousands of times of volumes of data, because you want more and more data to be supported. You expect large volume of data to be supported. Now, when you want large volume of data, gradually the automation is creating an environment where large number of devices are getting connected, and each device that you have is generating data. It has already started. People have televisions. 5 years back, nobody used television which was consuming data. But today, every television you have is connected to wireless LAN, and that gets again connected to for OTT channel. So that's something that has changed. And as consumer at the home, they expect about 10 Gbps of data as an endpoint. And the latency to be low, that means you don't expect a delay. Plus, what people also expect is a long battery life. With respect to 4G, in 5G, people expect that the battery would be at least 10 times higher. What happens as you move towards higher and higher data, the high-speed data consumes more power, requires more power to transmit. Because you have got a lot of data to be transmitted, these communications start to drain up battery. So you need a superior battery technology by which the battery can withstand this for a longer time, and the device life cycle with respect to single charge of the battery can be high. And people and engineers are working on this. Now, one thing that everybody is looking at is, as we work, as the demand for higher data goes up and up and up, you need higher bandwidth availability. And this higher bandwidth availability can come up with higher frequency transmission. Currently, the world works around 1 to 6 gigahertz as far as wireless communication or cellular networks is concerned. We work between 1 gigahertz to 3-4 gigahertz up to that. But then with time, because the data rate has to be more, and we expect higher and higher data rates to be available, what we are expecting is higher frequency ranges to be available, and we are looking between 30 gigahertz to 100 gigahertz as the frequency ranges for communication. This will create truly near infinity data rate. Let us remember that there is nothing called infinity in terms of data rate, because as the data rate requirement goes up, our expectations goes up, and the applications requiring data also goes up. What are the technologies we are going to use for it in order to achieve this data rate? One technology that is going to be used very often or undoubtedly is the massive MIMO. It is called multiple input, multiple output system, where you use multiple antennas at the transmitter and receiver to establish a communication. And you are looking at it not a simple MIMO technique, you are looking at a massive MIMO technique where each of the receiver, transceivers use tens and tens of antennas, going up to even hundreds of antennas. Then, because the data rate has to be high and devices need to be more, you need networks that can occupy a smaller space. So cells will become small. And one more character of this new technique that new demands is when people move, they should be able to get the services irrespective of where they are. So the network would start to move. So we are going towards higher frequencies. Some applications that would require these demands of data include D2D communication, which is device to device. It's currently the requirement of communication is between human entities. Maybe I want to download something, I want to transmit something, I want to talk to a friend or things like that. Gradually, this will become a smaller entity. What will take over is equipment and hardware wanting to use the network and communicate over the network. Devices will start to communicate between each other. Your car will talk to your home. You'll have a battery charger at your home. Your car has batteries. The car and home will talk to each other to find out how much charging is required. Your microwave will talk to other gadgets in the house. So gradually what is going to happen is different devices or different hardware, different home durable hardware are going to communicate with each other. Thereby, the requirement of communication is going to go up. And all these new technologies have to encounter with the existing technologies, which are 3G, 4G, and Wi-Fi. They have to coexist, because whenever you introduce a new technology, if the old technology is not adopted in a downward compatible manner, the technology won't get accepted easily. Now, looking at certain 5G parameters, we are looking at data rates of 1 to 10 Gbps, which is very, very large amount of data. A capacity of 36 terabytes of data per month per user. That's very large really. Today we are doing a few gigabytes of data. Today you could be doing something like 100 gigabytes of data per month. Generally, if you look at the WhatsApp that you use, you may be using about 1 gigabyte of data, because very often your telephone operator network you'll be getting about 1 GB of data per day. We're going to use wider spectrum. The energy consumption per device has to go down about 10% of today's consumption. The delay in the network has to go down. The devices have to talk between each other more often. But what is more important is the reliability in the technology. You are expecting a 99.99% reliable communication technique. Looking at everywhere coverage and the enhanced battery life of typically around 10 years. Today's batteries last for about 3 to 4 years, but we are looking at newer technologies where the battery capacity is higher, plus battery life goes to 10 years. Now, what are the challenges we have? The challenges are, the data that we are going to generate is going to increase massively. Why? Every house, every device, everything that we have around us are going to generate data and communicate with the world. So there will be avalanche of network traffic or volume of data. Next is the gadgets will start to communicate. The connected hardware, the home hardware, you will start to communicate between themselves. You can see that today also. When you take a photograph in a mobile phone, it immediately gets uploaded to a cloud service. If I have a security camera at my home, it is connected to the cloud through which I can observe the security camera. If I am transporting something, I should know where the goods are, and that's through a online communication. So it is expected about 50 billion devices are there in 2020, but this number is expected to rise sharply with time. So the number of communicating hardware devices are going to rise considerably. Excluding this, there will be a strong requirement for device-to-device communication and car-to-car communication. Device-to-device means gadgets will talk between themselves, and car-to-car communication in highways, the vehicles should communicate between themselves regarding safety, regarding traffic information, regarding weather information, and whatnot. So, if you look at this scenario, we are looking at high data rate network where everything that we have, whether it is network traffic, industry output, transportation, people availability at places, or mobile phones, everything will start to communicate between themselves. This communication is the key to next generation of wireless networks. So again, as the networks become more and more dense and you require more and more applications out of it, we want to make these networks more intelligent, and that is where again technology is coming into the requirement. And technologies like machine learning, artificial intelligence, deep network, learning networks have come. Now, looking at a bit of machine learning started as a topic called what you call as neural network. And if we go by the definition of it, which was given by Herbert Simon, who received the Turing Award in 1975 and Nobel Prize in Economics in 1978, he said, learning is any process by which a system improves performance from experience. Now, it's the characteristic of human beings and animals. Any living organism in the world learns by experience and improves its performance with experience. And machine learning is a technology by which computers try to automatically improve their performance through experience. Now, things have started from there and have moved and progressed. Now, the first initial time around 90s, 91, 92, 89, around that time, these neural networks started in a big way. Many people worked on what are called neural networks, and then there is a time when AI also came in, but that time the computational capabilities of hardware were very, very low. And for that reason, the technology did not pick up very fast. Even though the theory was available, people formulated the theory, but testing this theory and using it in a practical application became a far-reaching thought. With time, the computational power has gone up thanks to the Moore's law and the technologies that have changed in terms of CPU creation or CPU design, computer hardware design, and all that. Over the past maybe 30, 40 years, the computing power has at least enhanced by about 1,000 times. So that is what has changed the scenario of machine learning industry. Looking at the basic form of any machine learning network, we call it as a neural network. And the neural network is a network which is massively connected. And what it is connected? It is connected with large number of elements. Now you can see here, this figure refers to a network. These two are two smallest identity of a human neuron, which is termed as neuron, and it is the smallest unit of human nervous system. And each of these units resemble electrically to this. So what you have is a collector and a set of responses. These responses with a weighing factor or a multiplication factor come to the collector. The collector receives it, passes it through activation function, which is nonlinear activation function, and then creates an output. This output again is distributed to multiple units, and then the process continues. This is what a neural network is. Now, looking at technology again, in 90s or early 90s, this technology that was available, the best of the technologies could provide a simulation which simulates or emulates the working of a small worm or a grasshopper or a earthworm. But today we have reached much higher. Technology can emulate the working of much larger size animals and the way they think. Any network has got three important characteristics. One is how the elements are connected, that is called as connection type. Their network design comes from topology, and the method of learning is called learning technique. When it comes to connection type, the connection types can be static or dynamic. The network topology can be one layer, multiple layers, or layers with feedback. When there are a set of layers, one feeding the other, they are called multi-layer. A single neural element layer is called a single layer. And when you have a layer, multiple layers, and then each layer feeding not the next layer, but also some of the previous layer, it becomes a recurrent network. The recurrent networks are typically feedback networks. They have a feedback engine, and this feedback helps them to create certain advantages. Now, any neural network has few components. It has got what are called the computing elements called the neurons. It has got activation function and nonlinear activation function at the output of the neuron. Again, that depends on types, and ultimately they work in specific way. There are multiple types of neurons, and each neuron works in a different way. Now, our human body or human nervous system consists of large number of neurons, and these neurons are also called biological neurons or biological nerve cells. So these are called neurons or nerve cells. Now, what they do, one nerve cell, this is the input side of it, this is the output side of it. It takes the inputs, does the computation, and then passes it to output, and it goes to multiple other neurons. This is primarily the neurons that are physically or biological neurons, how they work. In fact, I remember reading this during my class 8 biology. But then, when it comes to engineering method of generating this in an artificial way, the technology has really taken a long time to come up. Now, if I look at the smallest of these building blocks, which are computational blocks, what I have is a small computational unit which calculates. I have a set of inputs. These inputs are multiplied with a set of weights and added. And then this output of the weighted sum is passed through activation function, which is a nonlinear activation function. That's the total of the network we have. Now, from input to output is a nonlinear mapping. This is a single neuron. When I have a series of such elements, they create what is called a multi-layer network, and then they give a different activity. And every neuron has an activation function, which is here. And this activation function, there are many types. It could be a binary state function. It could be a tan hyperbolic, sigmoid, or other types like partially linear and things like that. So any network would, when it works, it has to work with certain algorithms. Algorithm means the network first has inputs and outputs. When you have the input, you know how to calculate the output. But having done that, how the network tries to learn itself to find out something is dependent on the network design. One is different ways by which the networks learn to work is supervised learning, unsupervised, semi-supervised, reinforced, evolutionary, and deep learning. So these are the different types of learning techniques by which these neural networks work towards, or they learn to imitate a task and learn to accomplish a task. It's very similar to how a child learns to do something. It could be learning to eat, learning to drink, learning to read, learning to comprehend, learning to run, walk, and whatnot. Now, each of these techniques have their own merits and demerits. I think we skip that because we'll move into different things, other sections. Now, the machine learning have been used in few applications, and when we use applications, one set of application is called classification, then another set is regression, and third is called a clustering. Classification is an application where you take the input vector or the input signal, and then map this input signal to one of the groups of the signal. So here what you are looking at is a mapping between the input to output. I receive something. It's like I see a color. If I can recognize whether it is black, blue, yellow, red, or violet, it's a classification problem. But when you come to regression, it's a method by which you calculate an output. It's like function mapping. So if I know some information about a data, I get a new input, I should be able to predict what the output is. That's called regression. Clustering is a process where you group a set of inputs to one group and group a set of different input to another group. And when a new input comes in, you are able to map it to respective groups. It's like you have a camera, and the camera you use tries to, let's say, if we use, many of you or most of us have used Google Photo today. Now, when you use Google Photo, very often, even if you have clicked a photograph, the Google Photo is able to tell the person who is involved or who is present in the photograph. This is where clustering works, where it is trying to tell who the individual is. It is a process which is a nonlinear mapping between input to output. I'm not going into how the neural networks work because that becomes more details in terms of this talk and more fundamentals in terms of this talk. What I am going to do is move towards use of this machine learning techniques in different applications. Now, if we look at the application side, again, remember there is a limitation of time as well. We have about half an hour more to complete. Now, looking at this as a application side, this tells about different applications that use deep learning, machine learning, and these technologies. The one which is inside the blue circle, they refer to wireless communication domain, and the outer one contains all sorts of applications. Now, we have been working in wireless communication, so we have used that as the one. Now, if I look at it, some of the applications that we have worked, me along with my students, we have worked together are PAPR reduction. PAPR refers to peak to average power ratio reduction in wireless communication, resource allocation in wireless communication, modulation classification, interference control and interference reduction, cognitive radio, massive MIMO techniques, improving the quality of massive MIMO techniques, power allocation in a wireless communication, channel estimation. These are the major work that has been done by. Our work has been primarily in these areas. But if you look at worldwide, there are people who are working in numerous fields. This is a small list out of that. There could be, the fields could be n number, thousands and thousands of times of these numbers. Any field you look at mechanical engineering, civil engineering, electrical engineering, electronics engineering, material science engineering, any engineering field you look at, any science field you look at, there will be thousands and thousands of applications which use these technologies. Now, look at some of the applications. Now, in communication, there are different applications which use this, and one is machine learning in 5G. Now, machine learning is an important, what I would say is a technology which has got a lot of demand. 5G is another one which has got a lot of demand. And when you look at machine learning for 5G, there are quite a few work that is being done. And in terms of 5G, if I look at the machine learning side, there have been usage of supervised learning, unsupervised learning, and reinforced learning. And with that, different technologies have been used, where things like regression modeling, application in 5G, massive MIMO, and other things are available. So each of these categories tell what sort of application exists, and there are innumerable applications. If you look at the literature today and give a search word, you will find hundreds of articles looking at different subject areas and different applications in these fields. So we look at some of the application side. Application of machine learning for intelligent wireless systems, 5G and beyond. Basically, we are looking at some of the applications for 5G and beyond. Some of the applications that we'll discuss now include signal detection, modulation classification, channel estimation and compression, resource allocation, channel encoding and decoding. Some of these we will discuss and take a few case studies which have been worked or researched by some of my students. The first one is a signal detection. So in signal detection, our target is to receive the signal from a transmitter at the receiver end and take the signal and detect or try to determine what was transmitted. Now, in this specific case, what we have, the top box is the transmission box, bottom box is the receiver side, and this model is the channel model. Now, what we do is we do a simulation to imitate this transmission side, thereby create a replica of the signal that was achieved. With that, we can test whether the receiver we have is able to work correctly. And this process is called learning. And this process is called learning. And this is used, this technique is used in many of the application or the exact problem area that it talks of is the channel estimation and signal detection. And this technique has been used in wireless communication very often. And there are large, if you look at signal detection and channel estimation, there are innumerable work that have been conducted or done by people and published worldwide. Another example is called radio modulation classification. Now, whenever we receive a radio signal, whether our mobile does it or any radio hardware does it, essentially whenever we receive a radio signal and then want to detect what the signal was transmitted, what is the baseband signal that was transmitted, we have to first determine what type of modulation is used in the signal. The process of determining that modulation, is called radio modulation classification. It's a typical problem of classification where we receive the signal and try to estimate what is the type of modulation used, whether it's a QPSK, MQPSK, or it is a 256, 64, 16, what sort of it is, whether it is AM, whether it is FM, what sort of coding is used, and all these parameters of the signal that has been transmitted is determined. And very often this technique is called blind signal identification, because at the receiver is designed to detect any signal. But before it can actually do the decoding and detection, the receiver has to be able to find out what modulation format is used at the transmitter. And that job is done by what is called a process of radio modulation classification. Now, this helps in improving the spectrum utilization and minimize interference. Now, if the modulation variation is known or the modulation type is known, the receiver can do a superior detection, thereby providing better quality of service. Now, another area is in link adaptation in modern military intelligence systems, where one has to detect the frequency, the type of modulation used, cellular standards used, and other details. Now, this is again another classification technique where you use different classification techniques to find out what is the information sent. Now, if I receive the radio signal, it is not possible from the radio signal to determine what was transmitted. That is possible in AM and FM, but not in digital modulation technique. So here what is done is you use different techniques to find out first what is the modulation used and apply that modulation receiver technique to detect what signal or what was transmitted by the transmitter. Now, in a modulation classification, that region becomes quite important. What do you want to do in modulation classification is find out the type of modulation that has been used in the application. Now, take for example, I'm transmitting a signal which is QPSK, 16 QAM and 64 QAM. As my signal constellation goes up from QPSK to 64 QAM, the signal separation, constellation separation starts to move closer. Thereby, it start to become very, very close, and a small amount of noise can overlap the signals considerably. Under that circumstance, it is always required to do the detection of type of modulation used so that the receiver can fine-tune its parameter to do the best receiver, to provide the best performance. One such application, the block diagram is given below. It has been taken from the resource at the bottom, listed at the bottom here. Hello. Meeting. Sorry. So what we are looking at is a method by which we are able to extract and find out what is the type of modulation that has been used, and thereby find out the design a receiver to detect the signal. So what it does, it is primarily a method by which you are trying to classify the modulation. So this is called a modulation classifier. But to classify the signal, what do we use? Extract the signal and use some fusion technologies, which are intelligent methods or AI-based methods, so that the signal can be detected. And very interesting case. So you get the input which consists of multiple signaling systems, and then apply signal processing techniques to separate the signal, and then ultimately classify what type of modulation is being used. Now, today, when you look at a wireless network or wireless communication network, Wi-Fi network, or for that matter, a mobile network, depending on the quality of the environment, the data rate changes. Now, when the data rate changes, the hardware should be able to detect, the receiver should be able to detect what is the type of modulation being used by the transmitter. And this is what is used very often. And this should be robust, because unless it is robust and able to do the right, detect the right type of modulation being used, there are chances, or there are strong chances, that the signal will be wrongly detected, thereby the information would be lost considerably. Now, one technique where we use automatic modulation classification using deep learning. So you have the signal. When you receive the signal, how do you apply automatic modulation classification in a IoT network? We're talking about IoT network. In an IoT network, you have large number of devices that are collecting information. And from these devices, you all these devices that you have, they provide information. It comes to the gateway, goes to the internet. From the internet, we collect it and send it to the server and do all the computation to find out what sort of modulation is used in the network. Another example, deep recurrent convolution with gated unit. This is again a technique where we are using the deep learning technique to classify and find out the type of modulation that has been used in the signal. This is one of the what you call is cognitive radio application, where we get the signal, but from the signal that we receive, the receiver does not have information about what was transmitted or what modulation format was used. So use this to detect what sort of modulation was used in the signal. If this can be detected, then the signal can be detected at the receiver efficiently. We have used certain deep learning techniques. Now the network layer and all other details are given, and it's a full paper that have come out in a journal. And then with that, we found some of the results to be encouraging, and the paper has been published in last year. Now, very similarly, there can be other applications where similar things can be done. One of the measurements to detect these signals is called a confusion matrix. Now, what confusion matrix does is, I receive a signal. When I receive a signal, I predict. Imagine I have a signal which could be something like BPSK, QPSK, GFSK, QAM16, QPSK, and other things. Now, I had transmitted something and I tried to detect what was transmitted. If I can detect, if I plot my type of detection and type of transmission, if everything is fine, I should get a straight line diagonally because they both appear in the same line. But if there are errors, other places will start to show up. So this is called a confusion matrix. In a confusion matrix, if only the diagonal element is present, it is expected that the network performance is good and it is meeting the requirement. Now, next one is a different application where you take the RF signal, do some amount of pre-processing, and then detect the signal. What the work was deep learning based modulation classification using time and Stockwell domain channeling. Basically, what is done is, it is a modulation classification problem. Time and Stockwell are the two techniques that were used in this work. So again, it is a very similar thing. You get the RF data. This RF data is organized for a specific computational purpose, and then you feed it to finally find out the modulation type that was used. This paper has been was published in NCC 2019. Now, there are a large number of applications which use similar technologies, and there are many scientists and researchers who are working on these techniques. What we used in this work, we used different modulation classes. There are 10 types of modulation classes we used. We used a SNR range of -8 dB to 8 dB SNR, and then tried to detect what was there. These research problems have been worked by our students, and our some of them are faculty, and this should give you some idea of what sort of work being done in India with respect to this. Now, again, when you present it, you would present things as what is called as accuracy of the result, and the accuracy could be in terms of percentage. 100% accuracy is the best one, and below 100% is the lower one, and the lowest being here 65%. Now, again, this problem had its own confusion matrix and other things, and it was used and done. Now, Another example or a application area is called the channel estimation, prediction, and compression. Channel estimation is a process by which you find out the channel so that whatever the imperfection introduced by the channel are eliminated by using an inverse process. Then you predict the output and then also complete the data compression process. Now, this is one example. Another example where communication is being used. I'm not discussing the details of it. Another one is resource allocation. Resource allocation is an important area where the users are allotted. When a communication link gets established, some resources have to be allocated to the communication link. Now, if there are multiple users and then they want to transmit signal using different methods, what they have to know is what subcarrier each user gets and how much power they can transmit. These two, the amount of power and the number of subcarriers becomes two resources. Now, how do you, among a competitive set of users, n number of users, how do you share the resources among them is the problem area. Now, this is again a paper of 2019 where people have discussed about deep learning methods for resource allocation in vehicular network. Now, it's a wireless network area. Again, it's a deep learning technique that was used. Now, one more example is channel encoding and decoding using machine learning, where you transmit and then during the process, you estimate, encode the channel and decode it using machine learning. So at the transmitter, it has been encoded. At the receiver, you decode it using machine learning. This is another example area. Now, having looked at this, gradually we are moving towards 6G, and 6G is certainly going to bring in a lot more technologies into the system. Technologies in terms of application areas and technological areas. That will come up with time. Maybe by next 5 years, we should be moving into these technologies for use. Now, many of you are young and you would be looking at opportunities to work and creating a career in these areas. So, if we're looking at that, one should be working towards 6G networks and reading about 6G networks and working on these so that you catch it up early before many people come to do this. So for 6G, what are the things we are going to use or going to have are, or what are it that is going to enable the 6G technologies would be cell-free massive MIMO system. There will be no cells now. We are free to move around. Intelligent reflecting surfaces. This is the antenna side. This is antenna side. And federated learning approach to edge and IoT network. This is the intelligence side of the system. Intelligence side. Now, when the 6G comes in, these technologies will take precedence and start to give us better enabling experience in the application area. Now, one of the enabling technology is said that the 6G would be highly spectral efficient. Now, what is spectral efficiency? If you look at the left one, it shows the spectral efficiency going from something like 0.5 to 8. That means I can get something like 8 bits per hertz per user, but the minimum I would achieve would be fractional, 0.5 or 0.25. But when I go to 6G, I expect to have a minimum of 5 and maximum of 8. So my minimum spectral efficiency is going to become very high, and this spectral efficiency is the key to enhancing the data rate. Remember, 8 bits per hertz per 8 bits per hertz per second is going to be the large one. But in the 5G and 4G communication, even though the peak is 8 bits per hertz per user, but the minimum can go up to 0.5. But in 6G, we expect that the minimum floor will be much higher than what we had in 5G. This is what is going to provide higher data rate in the communication system. Again, another intelligent thing that would come up in 6G is intelligent reflecting surfaces, which would work as, these will work as antenna, some form of antenna. Thereby, the devices can work more intelligently and selective reflection of the data of the information would be possible with the help of intelligent antenna. This is one area which is attracting a lot of interest, and people are working on this so that they could use newer technology based antenna design so that the communication can be more efficient and more secure. Again, a similar area where you have intelligent reflecting surface. This is the intelligent reflecting surface, and the intelligent reflecting surface helps you to direct the signal in the right way. Again, when you have a lot of devices, we are going to have a lot of IoT devices, Internet of Things, and everything that we have in our house will have some transmitting device or the other, because IoT is taking over, and there will be measurement of every parameter at homes. It may take longer time for the technology to arrive at our homes, but then this will eventually arrive in not very long time. So when this happens, how the technology is going to work towards enabling this 6G will be the key to connect these devices, this massive number of devices, to the world. So essentially, we are going to have much more computation because the devices are increasing, amount of data being transmitted are increasing. So this wireless communication is going to take a lot more resources, and it would go ahead to bring in more technologies into the world so that the higher levels of achievements can be achieved. When you say higher level of achievements, I mean higher level of specification requirements of 6G can be achieved. I think I close my talk at that. I can take a few questions on this. We have about 10-15 minutes for that.
Yes, sir. So thank you very much, sir. Thank you very much for your insightful talk. You started your talk with the evolution of cellular communications, that is starting from 1G, and then until you touched upon 5G, and then you moved on to like what will be some of the technologies that will be included in 6G communication. So, for example, cell-free massive MIMO or these intelligent reflecting surfaces. So these are all the things like talk was in depth and it was in detail. So thank you very much for your presentation, sir. So there are some few questions from the participants side.
Please go ahead.
Yeah, I'll read out some few questions, sir. So most of the machine learning techniques are used for spectral efficiency, but whereas limited research is done on the energy efficiency. So why machine learning not much used for energy efficiency optimization in wireless communications? Like people are working on spectral efficiency, but not much research is going into energy efficiency. Yeah. So this is
to say I may not be giving the right answer to it, but this is a hunch I have. You see, the spectral efficiency goes towards enhancing the spectrum utilization. That means with a given spectrum, we are able to transmit more data. And this is achievable with spectral efficiency. Okay. Now, energy efficiency will help to harness the energy that is being wasted in our mobile phones or mobile or your devices. I would think the spectral efficiency is more important because to achieve, we are reaching towards a dead end, not dead end rather, we are reaching towards a limitation on the amount of data we can transmit over a given bandwidth. And we are trying to improve that. But as far as the energy efficiency is considered, the energy efficiency possibly we cannot achieve much more, because there is a certain level which you can achieve. If you look at the device, now what is the energy efficiency if I am using a mobile phone? The energy used in a mobile phone comes from RF transmission. That's a small component of the total energy being used in the phone. Now, my display takes a lot of energy. The computation in the device uses a lot of energy. They in fact use about 90% of the energy, and the remaining 10% may be being used by the transmission process. Possibly this is one reason why people are not looking much into energy efficiency, because energy efficiency is more important from the design point of view for a mobile hardware than the transmission and communication side. That's my feeling, but I could be slightly wrong. But I think this is what the reason is.
Okay, sir. Thank you, sir. And just one more question before I hand over to Dr. Satish. So, is these intelligent reflecting surfaces can reflect the exact signal, or will there be any loss? So, how we can able to?
Technology has to. Any technology we talk of will certainly have loss. A technology cannot be ideal in any case. There will be loss, and when there are challenges, human beings come up with innovative solutions to face these challenges. I think that would become an area where people will work towards improving the performances. Energy loss has to be there. It cannot be without it.
Right. Thank you, sir. Thank you very much. So over to you, Dr. Satish.
Okay. I agree with Dr. Sunil that, sir, you have really covered a comprehensive topic, just that too from 1G to 5G and beyond 5G. You have given flavor of this machine learning, deep learning, and advanced technology like this intelligent reflecting surfaces. So I am very confident that it's going to be very useful for our participants. And sir, I have a question. Sir, I have a question which is, since I am new to this topic, machine learning, I do not know much about it. So I have a small question that this ML or DL technique seems to be an intelligent algorithms for the processes like resource allocation, channel estimation, detection. However, these techniques can be complex. So, sir, is there any trade-off between the complexity and performance of these techniques or algorithms?
Certainly, yes. Okay, there are one part is when you start to build a network, when the network is small, your complexity is small, but the performance could be low. As you start to build the network bigger and bigger, you start to achieve better and better performance. Then what happens, a time comes where you get the best performance, and going for more complex network actually reduces the performance. This is where your numerical instability or the numerical approximations start to overpower the benefits. It's always the case.
Okay, sir. Any questions from the participants? Still, you can ask the question. You can unmute yourself and can ask the question if you have any. Okay. Since there is no question, we can conclude the session. Thank you, sir, for accepting our invitation. It was indeed a comprehensive talk, as Dr. Sunil and we have noticed. So thank you very much, sir, for your valuable time. We know, sir, you were busy during the presentation. Also, you are getting call. But really, thank you very much, sir, for this presentation. And I hope that this was very useful for our participants. And we are looking for some your physical presence in our university since this COVID period is over. So at times, sir, when you are free, we'll like to invite you to our university. And thank you very much, sir.
Okay, thank you. Can I disconnect?
Yes, sir. Yes, sir. Thank you, sir.
Thank you.
Just thank the participant.
Yeah. At the end, I will thank you all the faculties, the PhD students and participants who have invested a lot of time Today's was a hectic schedule. From morning to evening, we have 3 sessions. So thank you very much for your presence. Tomorrow and for the next 4 days, we'll having only sessions in the afternoon from 2 p.m. to 5 p.m. We're looking forward to your participations for those sessions also. Thank you very much.